Hi everyone. In this lecture, we're going to be basically introducing our last chapter, which is persistence. So that's what we're going to be looking into. And persistence, it refers to the characteristic of a state that outlives the process that created it. So through the processing of a particular process, it has either maybe saved something into storage, but it's just this general idea of that some sort of data outlives the process that created it. And this is achieved in practice by storing that state as data in some sort of computer data storage. And we're going to be looking at how storage is handled and how the operating system basically makes this process more efficient. Now, in the first half, we will discuss our input-output devices and how the overall structure of our hardware interacts with these devices, how that looks like, as well as the storage devices like I mentioned already. And lastly, in the first half, we'll be looking at the process of abstraction that takes place in order for interaction between these devices to be efficient and simple for processes to interact with. So if you remember, like we talked about this idea of abstraction throughout this course, whether it be abstracting our process, or basically abstracting the CPU into what we call the process, abstracting our RAM into our address space, our memory into our address space. So once again, this is just the same idea of our virtualization, adding that additional layer that allows us, basically that acts as a border for which like our actual physical hardware can therefore interact with our like user processes, and that is provided by our operating system. So the second half of this lecture, so part 2, will actually describe how a file system is implemented, and we'll talk a little bit more about what a file system is just before we get into that. So just a quick recap, very quick. Last week we finished up on our concurrency chapter, and that was where we looked at conditional variables and semaphores. And these were basically alternate approaches to enforcing our critical regions. And that was the idea that we need a way or some sort of object or data structure that allows us to enforce a specific region's atomicity, or that idea of an atomic operation, meaning that when this operation is being performed, it is the only, it is only being performed by a single thread. And those alternate ideas were our conditional variables and our semaphores, and these were alternates to our locks. So to get into it, we're going to be first looking at our input-output devices. So input-output is obviously critical to any computer system, and that's because we need to have a way of interacting with these systems. Now, the issue that arises is how can we integrate our input-output devices into our systems? What are the general mechanisms for doing this, and most importantly, how can we make this process efficient? So the general structure is what you can see before you, and that's what we're going to begin our discussion with. So this is a classical diagram of a typical system. So obviously more like specialized systems will vary from this overall approach. But what you can see here is that our system has a single CPU which is attached to our memory, so it's connected via what we call a memory bus. So it's attached to the main memory of the system by this memory bus, and it allows us to actually communicate. The bus allows the communication. That's where the data actually is transferred along. And some devices are actually connected to the system via a general I/O bus. And these are our other hardware devices, such as our graphics card, or our PCIe and our PCI cards or slots. And you can also have some other like high-end performance input-output devices might be found on this general I/O bus. Finally, as you can see, even lower down on this like structure, we have our peripheral I/O bus, or just simply the peripheral bus. And this is where you'll find stuff like SATA, USB, SCSI. So these are all like basically all the rest of your devices, your actual hardware devices. So SATA is basically referring to any SATA connected device, like a hard drive or some sort of SSD. Obviously USB, you guys are familiar with that. And this peripheral I/O bus basically connects slow devices to the system, including mice and keyboards as well. Now, a question you might ask yourself is, why do we need like this hierarchical structure? Why do we need various different performing buses? Because our memory bus, our proprietary bus, it's actually the fastest performing bus. Our peripheral bus is the slowest, and the general I/O bus is basically in between there. So why do we need this hierarchical structure? And the reason for that is basically as simple as just physics and costs. So the faster the bus, the shorter it has to be. Thus, like a high performance memory bus, like up here, it can't be very long. And in addition, like the engineering behind a bus that is like operating at a high performance is quite costly. So that's why you can only afford really to have you can't really afford to have all your buses operating as like these high speed, high performance buses. Thus, system designers have opted for this like hierarchical approach, because these devices, they don't really need to be operating at high speed. So they're also a lot larger. So these, like our SATA, our USB drivers, stuff like that, are bigger. Additionally, with our graphics card, so there's not that much space to have them closer to the CPU, right? So just in terms of like the physical design and layout of a computer, they can't be right next to the CPU, which requires them having a longer bus. So again, that goes back to the idea of, well, if you have a longer bus, it's going to be pretty costly to have it as a really high performance bus. So where the demands require high speed, there's high performance buses, and where there isn't such a greater demand, or the bus requirement requires a longer bus, well, then you have a lower speed. Now, what exactly is a bus? Well, simply put, it is a data channel, a data pathway that enables us to transfer information between our various devices like CPU, RAM, or the actual input-output devices. And it is in the form of basically a cable, a wire in essence, but it's etched into your motherboard. And it basically allows a electronic signal to flow along it. And based on the signal, you'll get your binary information. I'm not going to go too much into that, but that is basically how the data is transferred along this bus. Now, the input-output bus, like I've already mentioned, so I won't go over this again, is basically just the data path that connects the CPU to our input-output devices. Okay, so let's have a quick look now at what we call a canonical device. So this is not a real, actual, specific device, but it serves as what, in general, all devices basically have or are represented by. And this canonical device has two important components. The first being our interface, and the second being the internals. So the first is the hardware interface, like I said, and it is the first thing that is presented to the rest of the system. So whenever we're communicating with our hardware device, this is like the first thing that we actually interact with, the interface. And this is just like a piece of software. Hardware must also present some kind of interface that allows the system to control its operation. So what do we use the interface for? Well, it is utilized to allow system software to control its operation. Thus, all devices have some specified interface and protocol for typical interactions. Like if it's a keyboard, then in interacting with like detecting keystrokes and stuff like that. Mouse, like mouse clicks, etc. The second part of any device is its internal structure. So this is the part of the part of the device which is implemented in a specific way based on that specific device, as well as the specific company. So not all keyboards or mice or screens are obviously exactly the same underneath. So this is, like I say, the internals, right? And this device's implementation is specific and is responsible for implementing the abstraction that the device presents to the system. So the way that these internals are represented also is what we utilize in order to interact with it as a general like user software program. So the idea here is that, well, we have lots of different hard drives, right? Different manufacturers of hard drives, different sizes, different write speeds, etc. But no matter what, when we're writing a program, we'll use the same functions to like write to that file, write a specific file on that hard drive, or read a specific file from that hard drive. And this generalizability is thanks to the specific implementation, as well as the operating system, of course, in our internals component. Okay, so that's just a general overview. That's just a general overview of all hardware devices. Now, just specifically in terms of that interface, we saw our status command data. These are all registers, right? So they store information in these registers. And the status register basically lets us see the current status of the device, whether it's being used or it's busy doing something. There's quite a few different statuses, or if it's available is another one. The command register, well, this allows us to tell the device to perform a certain task, whether it be like read writes for hard disks or other, obviously there's other different tasks that other hardware devices perform, but this is where we basically indicate to the device what task we want it to perform. And lastly, the data register, and this is where we pass information directly to the device or get information from the device. So if you, in a keyboard example, if you press a key, well, you'd store that key's information in the data register so that maybe a word processor could then obviously interact with the data register to get that key value and then for print it to the screen. And that's basically what the data register is for. So once again, if you remember, what is our hardware interface? Well, it's basically what we use to control its operation. Okay. So that's what you can see I'm basically referencing here. Now, a typical example of this is what you can see here, utilizing like that status. While the status is busy, then you'll wait. So let us describe this typical interaction in a little bit more detail. So this is the interaction like an operating system might have with a device in order to get it to do something on its behalf. So this like protocol or this like functionality here has 4 steps. In the first step, you see here this like while loop. The operating system waits until the device is ready to receive a command, and it does this by like looping in this while loop and repeatedly checking that whether our status is busy or not busy. So we call this polling the device. So it's basically continually checking, are you done, are you busy, can I use you, over and over again until it's available. Secondly, the operating system sends some data, okay, that's over here, down to the data register. So we write some data to the data register, and this is some data that the hardware device can then utilize for its own purposes, depending on which device it is. So one can imagine that if this were a disk, for example, and multiple writes would need to take place to transfer say, a block of information to the device. So if you wanted to do that, well, you'd store that information in our data register over and over again, or sequentially. The third step is basically the operating system writes a command to a command register, and doing so implicitly lets the device know that both the data is present and that it should begin working on the command itself. So you write the data first, then you issue the command to do something. And issuing this command tells the device to get going. And lastly here, we then check it once again, but this time we check in to see if it's finished. So the first check here is to check if it's available. And then the second check is basically, well, now we're going to wait until the device has performed some operation. And once it finally kicks out of this loop, we'll know that, okay, it's done processing our request. So when the status is no longer busy. Okay, so that's how a typical interaction between like the CPU and some specific device would take place. Now, I briefly mentioned that idea of polling. Now, here we see operating system waits until the device is ready by repeatedly reading that status register. And that was that while loop, right? That's that there. But one can already see that this is quite inefficient, right? Now, the positive side of that is that, well, it's simple and it works, right? You wait until the device is finished by just constantly asking, are you done, are you done, are you done? But what ends up happening is the CPU is not doing anything during that time. It's just checking. So the idea here is that it wastes the CPU time by just waiting for the device. And we saw this idea when we were talking about scheduling, right? When we said waiting for I/O. That's exactly what this was. So we've just expanded this idea out a little bit, that waiting for I/O is basically this idea of polling. And polling is waiting for it to be finished by checking the status register over and over again. So we already know that the solution to this is to switch to another process for better CPU utilization, right? And that is exactly what we do, right? Instead of using polling, we use our interrupts. And instead of waiting all the time, we just swap in another task, task 2, for example. So just to go through this, put the IO request process to sleep and context switch to another. When the device is finished, wake up the process which was waiting for the IO to finish through another interrupt. Now, the positive is that the CPU is busy all the time, and the disks are properly utilized, right? We only process task 1 after we finish task 2, and we have a better utilization of our disk here because we're using the disk while task 2 is actually being processed. So that does bring us to the question of, well, when do we utilize polling, and why not just always utilize interrupts? So interrupts is not always the best solution. If a device performs very quickly, the interrupt will slow down the system. Why? Well, there is a cost to switching to that other process, right? You have to perform an entire context switch. So the general idea is, if a device is fast, then we utilize polling. If the device is slow, interrupts are better. So that's just a general idea there. Now, there's an additional case. So unfortunately, there's one other aspect of like our canonical device protocol that requires our thinking. And that is in particular when we are using programmed I/O to transfer like a large chunk of data to a device. So say we were doing some sort of operation, but we needed to transfer a large amount of data to like memory or from one location in a disk to another location. In this case, the CPU is once again overburdened by performing this large copy of data. Now, it wastes a lot of time and effort that could be better spent running other processes. And you can see this illustrated by this timeline here. Currently, while it's copying the data, it's not actually doing any process, it's just performing the data copy process. And this is just the time between transferring data from our memory to our storage. And you remember I spoke about we transfer data along buses? Now this would be over a longer bus that is operating at a slower capacity. So during this time, we can say send the packets like in the beginning here, or the chunk of data, and while it's traveling across to its location, the CPU is basically not doing anything. It's waiting for that to occur. So once again, in this little period of time, our CPU is dormant. So just to explain this, maybe explain this example a little better, process 1 is running here and then wishes to write some data to the disk. It then initiates the I/O, which must copy the data from memory. So it's copying the data from memory to the device, one like word at a time, for example. When the copy is completed, the I/O actually begins on the disk side of things, okay? And then the CPU can then finally be utilized for another task. But this is the issue here, the overburdened component here of waiting for that large copy. So the solution to this problem is something we refer to as direct memory access, or DMA. And a DMA engine is essentially like a specific device within the system that orchestrates the transfer between devices, or the transfers between devices and our main memory. And this allows the CPU to basically not have to deal with this process. So the DMA is handling that copy between our devices. So it works as follows, right? To transfer data to the device, for example, the OS would program the DMA engine by telling it where the data lives in memory. So it'll tell the DMA, it'll send the location in memory where the data lives, how much data to copy, and which device to send it to. So which storage device to send it to, which input-output device to send it to. At this point, so that would be happening like over here, right? It would send all the information to the DMA, tell it exactly what needs to be done. And at this point, the operating system is done with the transfer and can proceed with other work. So that's what you can see here. It's proceeding with other work. Okay. Now, when the DMA is complete, there's a special DMA controller that raises an interrupt. So we've talked about like timer interrupts and all other kinds of interrupts. This is just another kind, right? The DMA raises an interrupt, and therefore the operating system knows that the transfer is complete. So at this point here, the DMA will raise an interrupt indicating that the transfer has completed. So now this is basically what our revised timeline looks like. You can see that our DMA is handling the copying, right? So CPU is much more utilized. The disk components basically stays the same. So this is a lot more efficient compared to this timeline here, where in this period of time, the CPU is not doing anything, but it could be. So that is the DMA. All right, moving a little bit on to our device interaction, or how the operating system communicates with devices. Now, the solution to this question is basically two components: input-output instructions and memory-mapped input-output. So in terms of the first one, these instructions specify a way basically for the operating system to send data to specific devices, to specific device registers, and thus allow the construction of, thus allow the construction of protocols in order to perform tasks. So an example of a protocol, I know I'm going back a bit here, would be this. This would be an example of a protocol that allows us to perform some sort of interaction. So it's basically just like a set of instructions that allow us to perform like a task, like basically a program. And an example of this on like the x86 infrastructure is our in and out instructions. So for example, to send data to a device, the caller specifies a register with data in it and a specific port with that names the device, so like the name of a hard drive. So now you have the data and the name of the destination, and you'll utilize our in and out instructions whether you want to send information to a device or get information from a device. Now, the second method to interact with devices is known as memory mapped input-output. And with this approach, the hardware makes device registers available as if they were memory locations. So just like we access data in our memory through like addresses, here we basically access our specific hardware devices through addresses. To access like a particular register, the operating system issues like a load to read that information, or a store to write information to the device instead of main memory. So this is something maybe you're more familiar with, because this translates directly to like our machine instructions or like those assembly code instructions of load and store. And it's basically applying that exact same approach of interacting with memory as if we're interacting with like storage devices or input-output devices. The next question you might be asking is, how does the operating system interact with different specific interfaces? Now, I mentioned we have lots of different companies, lots of different types of devices, all with unique characteristics. How does the operating system actually interact with these different specific interfaces? Well, let's just think of in terms of like specifically disks. Well, we would like to build a file system that worked on top of all of these, right? And they worked no matter what type of hard drive or disk like USB or CD you had. Well, the solution to how we can actually accomplish this is abstraction. And abstraction encapsulates any specifics of a device's interaction and basically wraps it in, for lack of a better word, a wrapper. And basically it becomes like a separate layer, right? Instead of interacting with the specific device, we interact with this abstracted layer. And then from the layer it gets translated to whatever the specific device needs. Okay, so let me explain a little bit better what I'm talking about when I say layer, as well as what is a file system. So the file system is that abstraction from our hardware devices, okay? And that's what basically forms the barrier, or there's a barrier between our file systems and our actual application. So what our applications do is they interact with the file system, and the file system basically handles the rest of interacting with the hardware devices below it. So here we can see a small example. We have our user application, and then if we wanted to, like, say, open a file, we would use this generic function called open, or read and write and close, etc. And this is independent of what the underlying hardware is, right? And you can see we utilize this API. And I think I briefly discussed our input-output API way earlier, but it operates in the same way as like when we talked about our thread API. Or our process API. You know, we utilize a single function to create a process regardless of whether we have a specific CPU or not. And the same goes for our thread API. So why would it be any different for basically our file system API? And it's not. So after we actually like call our open function or read function, it then is handled by the file system, And that will issue like a read and write request to what we call this generic block layer. So that's what you can see here, block read, block write. And inside this layer, there'll be a specific protocol which interacts with the specific hardware device through what we call a driver. So it's basically a chain of interaction, but as a user process, all we see is the file system. Now, there is a problem in terms of file system abstraction, and that is if like a device has special capabilities or has like some special functionalities, these capabilities will go unused in the generic interface layer, right? This generic layer cannot account for all the specific different interactions or different functionality that specific hardware devices could perform. And what that has resulted in is that an over-reliance of device drivers. And a device driver, to put simply in computing, is like a program that operates or controls a particular type of device that it is attached to. If you check back in our diagram, it is the last like layer between basically our application and actual hardware devices. So it sits closest to the actual hardware devices themselves. And most of these drivers will be built by or designed by the company or the manufacturer of that specific device. So like I said, this has resulted in the over-reliance of device drivers, meaning that in today's operating systems, like 70% of the code is found in device drivers. Now, these device drivers are needed because you might want to plug in a specific device into your system and you would like it to work, no matter what that device was. And because we've got so many of these different device drivers now, and the fact that they are designed by like companies, they are the primary contributor to the kernel crashes, as well as making other bugs occur as well. Well, what makes up a simple driver? Well, here we're going to be talking about like a simple example of a IDE disk driver, and it has a few different components. So it has a control, a command, and status and error registers. It also has memory maps I/O, like we discussed earlier, as well as an in and out I/O instruction. So this is what is utilized to basically communicate with the device. Now, just to explain a few things in greater detail here with these examples. So say, for example, if you wanted to wait for the device drive to be ready, you would read that status register, right? Just like we saw before in that example of that protocol. If you wanted to write parameters to command registers, you would write the sector count, the logical block, the address, and various information to the command registers. And these specifics aren't super necessary, but they're here for you to see. Now, if you wanted to start like an input-output operation, you would issue a read and write to that command register, right? Just like we saw in that protocol. So you can see how these different cases can be handled by just our four primary types of registers. So this is a very overview look at a disk driver in terms of like a theoretical look. But yeah, that's basically how they work, by communicating through the use of registers. Cool. So moving on to getting more into detail with our abstraction of like storage. And that is through the use of files and directories. So two key abstractions have developed over the time in virtualization of storage. And like I said, the first being files and the second being directories. And this is abstraction in terms of our hard disks. Well, the first one is the file. That's what we're going to be looking at now. And that is a simple array of bytes, each of which you can read or write. And each file has some sort of low-level name, and we call this, well, it's usually denoted by a number of some kind, and the user is often not aware of this name. So this name is like hidden. You can obviously display it, but it's hidden. It's not the name of the file. It's an identifier that's hidden. And we often refer to these as inode numbers. So each file has a single inode number associated with it that the user is not aware of. And in most systems, the operating system does not know much about the structure of the file. So what I'm talking about here is like, it doesn't know whether it's a picture or whether it's a text file or some seed code. Rather, the responsibility of the file system is simply to store such data persistently on disk and make sure that when you request the data again, you can get what you put there originally. So like it says here, the file system has a responsibility only to store the data persistently, not to understand the inner workings of what the file is. So the second abstraction is that of a directory. A directory, like a file, also has a low-level name, so it has its own inode number, but its contents are quite specific. It contains a list of user-readable, low-level name pairs. Okay, so what does this mean? Well, let's say, for example, there is a file with a low-level name of 10. So basically an inode number of 10, okay? And it is referred to by the user-readable name of foo. So foo would be like the file name that you would see normally, and 10 is the inode number. So the directory contains a list of pairs like this. Now since a directory has its own inode or low-level name, it will also have its own user-readable name. So foo could be an actual directory itself with the corresponding low-level name of 10. So each entry in a directory refers to either files or other directories. And by placing directories within other directories, users are able to build an arbitrarily long directory tree or directory hierarchy, and under which all the files and directories are stored. So this is what we call our root directory. And from our root directory, you can basically all other directories can be reached. So if our root directory is indicated by this slash here, foo will be on like the left-hand branch, bar will be on the right-hand branch, hypothetically. And these are both directories within the root directory. All right. Now foo has a file within it called bar.txt. And this bar directory has another bar directory within it. So directories and files can have the same name as long as they're in different locations in the file system tree. Okay, now I'm not saying there's only two branches. You can have many more branches here. This is just a hypothetical example. So let us now discuss the file system interface in a little bit more detail. We'll start with the basics of creating files, and that's the example that we're going to be looking at, accessing them, as well as deleting files. Now you may think it is straightforward, but as you'll see along the way here, there is a slight mystery that we'll reveal in time, and that is known as unlink. And we utilize unlink for removing files, so we'll get back to that in a bit. But yeah, it's not as simple as you think. Now, one important aspect of open, which is what is required for creating files, is what it returns. Now, open doesn't return like a file, but it returns an integer. And this integer is a file descriptor, and it is private per process. So the file descriptor, if say you have multiple threads, and you should have noticed this already, if you have multiple threads opening files, this integer variable will actually be unique across those threads, even if they're opening the same file. So like I said, this integer variable is private per process, and it is used in our like a Unix systems to access files. Thus, once a file is opened, you use the file descriptor to read or write from or to the file. So the file descriptor is an integer and is used to access the files themselves. Now in this, there's a couple different flags that you use, like this one here for creating, but you don't really have to understand that. Just understand that it returns a file descriptor, which is what we actually utilize to read and write. And that assumes that we have the permissions to do so. Now here's that example for reading and writing. And here we're specifically reading and writing to the foo file. And we can actually in the terminal use a couple different functions to perform this task. So echo redirects the output of echo to the file foo, okay? And cat dumps the contents of the file to the screen. So if you say echo hello, it will basically store this text or this data in foo. And if you say cat foo, well, it will take whatever's inside foo and put it to write it to the terminal. Renaming, basically the rename function takes in a couple pointers to char variables, and it's basically like a string of characters that this is performing or using in order to rename a file to a different name. The only thing that's really important here is that you understand that this is an atomic call. Now, why would it need to be an atomic call? Well, the reason for that is, say you wanted to change the file name, but while you're performing that file name change, another file accesses either the new name or the old name. This could definitely cause some issues. Okay, so let's move on to the more interesting stuff, not just using functions that we basically understand already, but moving on from that. So the first one I'm going to be looking at is hard links. And here we're actually going to be revealing that mystery of why removing a file is performed via unlink. And this will become a lot more easier to understand when we realize or understand how the function link works in the first place. And this is a new way of making an entry into the file system tree. Now, the link system call, what it does is it takes two arguments, okay, an old path name and a new one. And when you link, hypothetically, like so, link in quotation marks, a new file name to an old one, you essentially create another way to refer to that same file. So the command line program ln, so this ln, is used to do this. And you can see in this example what is happening. We perform that same echo hello, so we store in hello in file. We then say cat file, so that's going to print hello to the terminal. And then we say ln, so we're linking file 1 and file 2. So we're creating a hard link, and that's going to link file to file 2. Okay, and then we say cat file 2, and you can see it outputs hello. But we didn't store anything in file 2. But what we've actually done is we've made a link between file and file 2, so they're basically the same file. So the way link works is that it simply creates another name in the directory you're creating. The way link works is that it simply creates another name in the directory you're creating the link to. All right, so another name in the directory you're creating the link to. So the other name was file 2. All right. And it refers to that same inode number. So what you'll see here is that file 2 and file will have the exact same inode number. Now the file is not copied in any way. Rather, you just have two like human readable names, file and file 2, that both refer to the exact same file. So this is better described or demonstrated here, is if we want to actually display the inode numbers, you can use this command ls-i for other and then the file names that you want. And you can see the inode numbers are exactly the same. So they're referring to exactly the same file. So that brings up the question, well, what happens when you delete something, right? What happens when if I delete file? Is file 2 still okay? Well, that's that mystery of, well, why do we use unlink instead of remove? So thus, to remove a file from a file system, we call unlink, and that basically removes that link, right? Or in a sense, at least. So in the example that we've demonstrated here, we could, for example, remove the file name file and still access the file without any difficulty. So if I say rm file, I've removed file, and if I go cat file 2, which is what we linked to file, it still prints hello. And that's because behind the scenes unlink is being called when we use this rm function. So we're still able to access it. Now the reason this works is because when the file system unlinks a file, it checks a reference count, okay, so how many files are linked to it basically, and it checks this reference count with based on the inode number. This reference count is sometimes called like a link count, so the number of links, if you want to think of it that way. And it allows the file system to track how many different files, it allows the file system to track how many different file names have been linked to a specific inode. So before, when we had linked file and file 2 to a specific inode, well, that link count would have been 2. And when we call unlink, when we're trying to basically remove a file, this basically removes one of those links and decreases that link count or that reference count. And only when that reference count reaches 0 will the file system free the inode, basically actually deleting that file, as well as the related data blocks. So it actually truly deletes the file. Now here is basically a nice demonstration of what's happening there in terms of the links. And you can use stat, which is another like terminal function, to show the reference count of a file. So in this example, we create 3 links to the same file and then delete them. And you can see the link counts change over time. So here we just basically store into hello in file, and then we say stat file, and we see, oh, okay, there's only 1 link. We then link another file, there's 2 links. We also display the inode number, we can see 2 links. We do another link with file 2 and 3. So now there are 3 links, and then we remove the original file. So there's 2 links, we remove file 2, there's 1 link. And then finally remove file 3, and then there would be 0 links. So you can see how links are a much more efficient way of storing duplicates of the same file. Now the last thing that we're going to be looking at in this part of the video is another type of link that is really useful. And it is called a symbolic link, or sometimes it's often called a soft link. Now, hard links are somewhat limited, and that was because you can't create one to a directory. And the reason for this is the fear that you'll create a cycle in the directory tree. So you'll have like one directory or one link pointing to a higher node in the same tree, and therefore generating like a circle. Like a circle setup or a circle reference, a circular reference. Now, the other case is you can't hard link to files in other partitions. So what this means is that if you have multiple partitions, these are essentially multiple file systems. And because they're multiple file systems, files in these other file systems would have a unique inode number. And because the inode numbers are unique, well, you obviously can't hard link to them. And so because of these 2 issues, a new link was created called the symbolic link. And it's pretty easy to use or to implement or to create, sorry. And that is by just simply adding this -s flag to our ln function once again. So if we just do ln file 2, we'll do the hard link. To do the soft link, ln space -s file and file 2. And you can see it's performing the same. It's resulting in the same output like we saw before. Now, the first difference between the symbolic link and a hard link is actually that symbolic links are files themselves, but of a different type. Now, we've already seen regular types of files as well as directories, but our symbolic links are like a third type. And if you use the stat function once again, you can see this demonstrated. So if we did stat file, it says that it's a regular file, and if we go stat file 2, it indicates that it is a symbolic link. Another thing to note is that if we run ls, it also reveals this fact. And that is because if you look closely at the first character of the long form of the output, so over here, which indicates like your read and write information, you can see that the first character for the regular file, or just file, was just a dash. The directory, well, that's D, and for file 2, that's a link. Or sorry, it's L, indicating a symbolic link. And you can also see that the symbolic link is 4 bytes in size. Or here you would see the size of the symbolic link, and in this case it's 4 bytes. The reason that file 2 is 4 bytes is because of the way the symbolic link is formed by holding the path name of the linked to file as the data of the link file. So the name of our link file is file 2, and the data inside this file is basically the path to file. And because we've linked a file named file, our link file, file 2, is small, or 4 bytes. If we had a longer path name, our link file would be larger in size, right? These are both in the same directory, so it's relatively small. But yeah, like I say, longer path name, larger size of link. Now, finally, because of the way symbolic links are created, they leave the possibility of what is known as a dangling reference. So this is the slight issue or downside to symbolic links. So as you can see here in the example, it is quite unlike hard links in the sense that removing the original file has actually caused the link the link to point to a path name that no longer exists. So to demonstrate or explain this a little bit slower, we do that whole echo file thing. We then symbolic link the 2 files together. We output a file 2 and it works, right? Hello is printed. But then when we remove file and then do the same thing, since file 2 is using this path to the other file as a way of referencing it, since that file no longer exists, we get this issue that no such file or directory exists for file 2, even though it's there, it's just pointing to the wrong location. So this is what we call a dangling reference. And that is going to be what we end on for this part. Just basically getting into the understanding of talking about files and directories, this abstraction, as well as how input-output devices fit into the overall structure of our CPU, memory, all of that type of thing, as well as what are the functions that we utilize to interact with various storage devices or input-output devices like reading, writing, loading, storing, and stuff like that. Like I said in the beginning, in the second half, we're going to be looking at an actual implementation of a file system and running through quite a few examples to demonstrate how access to information actually is performed, or in terms of like registers and stuff like that. So I hope you understand, and I'll see you in the second half.